finish up what we were discussing last time, I wanted to wait until Shachi got here so that we'll have some recording of this. Okay? So what we're going to do is we're going to finish up our discussion of the min cut. Okay? So let's see. Okay, so remember what we are doing. What we are doing is we are applying this squishing operation, right? So merging vertices, right? So for instance, we took this and if we merge these two vertices, then we end up with this. So the way we, you can easily understand this as a squishing, which means that all the edges that are coming, let's say if there was an edge coming here, that will now go back to C. Okay? And that is more clear, when we squish B and E, right? So B and E have been squished into one node. All the edges coming into either B or E now go into B, right? So this is the operation that we are doing repeatedly. So let's see what happens when you go to a graph like this, right? And let's say this is the min cut, okay? Let's say you squish all these nodes together, right? And then you also squish all these nodes together, right? So what's going to happen? You're going to end up with one node on the left, which is called ACDG, right? Right? The squishing is sort of intuitive, right? So you just collapse, right? And ADCG are going to collapse, and then BEHF are going to collapse, right? Now, when you collapse, obviously you're not, although you are allowing multiple edges between the same nodes, you don't have self loops, so there are no self loops coming into those. But the three edges that are marked here in red, right, or at least the cut set here, right, they go from here to here, right? They would have been squished, right? Because you have basically taken all these and squished them together and done the same thing here, but that still leaves these edges with one end on this side and one end on the other side, right? So they are not going to be collapsed because they are always, they have one end on each side, okay? So this is why when the whole process is done and you have just two nodes, right, whatever is the set of edges that are left, those represent a global cut set, okay? So let's try to understand it maybe in another way so that we have perhaps so let's say you have a graph, right? And right? So the definition of a cut set is that you can sort of divide up the graph into two parts, right? And then the cut set will be all of the edges that are going in between, right? So this is the cut set, right? So this is a big graph, and we have divided it into sort of two components. This is component A, and this is component B, and then there are edges that are going between the two components, right? So this is our cut set, right? Now, of course, the whole question of is that the min cut, that's a separate question, right? And that it's only a probabilistic argument that what we end up at the end is a min cut, okay? But what we need to understand is that when this process finishes, it does identify a global cut, okay? And so, again, the way to understand a cut is you take the graph, divide it into two components, and then anything that goes across the two components, that's going to be a cut set. Okay, that's the definition of a cut set. Now, in terms of edge collapsing, what we are doing is we are collapsing everything over here into one node. Same way we are collapsing everything over here into one node. Okay, and then what we will be left with is this cut set essentially connecting these two. Right? So that's why the algorithm ends up, when it finishes, what it produces is actually a cut set. Okay? Now, any questions? Yeah.
So there could be instances where instead of collapsing as in these two, we collapse across one of these min cut edges. So those are the cases where you get a non-min cut.
Correct. So again, I want to answer that question in two ways. First of all, the reason why we do it in this way is because we wanted to say that the only things that are being collapsed are things that are here and over here. Right. So if in other words, this. You can think of this picture as having been drawn after you did all the collapsing, right? So when you did the collapsing, you keep track of what are all the nodes that you are collapsing this thing into, right? In this case, we kept track of it and said, okay, this is the node that we got from ACTG. This is what we got from VEHF, right? So once we have this final thing, we can easily say, okay, this VEHF, okay, that is this part of the graph. So we can actually identify what this, wavy line encloses, right? When we finish the recursive collapsing process, at the end we can say, what is this partition and what is this partition, because the vertex already says what are all the vertices it is derived from. Okay? So instead of thinking about it as drawing these boundaries in the beginning and then hoping for the best, instead think of it in exact opposite way, which is that what we are doing here is we are representing what the algorithm is doing. Right? The algorithm is collapsing one set of vertices into this vertex and another set of vertices into this vertex, and then we just now draw this wavy line around whatever set of vertices that have become turned into this one vertex. Okay? So now the question, of course, is, okay, so that tells you that this is actually a cut set. You don't know for sure that it is a min cut, and in order to be sure that it is a min cut, well, what can you do? Well, let's say you don't even want to make a probabilistic argument, you want to make sure you want to do okay, the definition of min cut is just in terms of number of edges, right? So you know that if you have two solutions, one solution has 4 edges, another one has 3, well, you know the min cut cannot be 4, right? So the minimum that you get at the end of this process is going to be the min cut, right? And if you repeat it enough number of times, then you can have a probabilistic argument that you would have, ultimately come across the min cut and picked it up. Okay? So again, the algorithm has two parts. One is to understand why at the end of it, it at least gives you a cut set. And once you understand that, then the rest is some mathematical analysis, which I will very quickly summarize again. Right? So what we are saying here is the high level point here is that the cut set has a small number of edges, and the graph itself should have a certain amount of connectivity, or else the cut set will be even smaller. And based on that, we are able to say, okay, what's the likelihood that the edges that belong to a cut set, min cut set, were not collapsed? Okay, and that is this analysis. And the analysis gives us a very small number. And so what we end up doing is we say, okay, in the beginning there are a lot of edges, right? So we say basically there are nk edges, and this is only k, right? So we say that there are nk edges. So if I pick at random, the chances that I picked one of these, because if I pick one of these edges, then of course I collapse them, right? So I'm lost. I no longer have the min cut anymore. So I need to make sure that I leave out these edges that belong to the min cut, right? and then I can probabilistically analyze if I pick edges at random, what's the likelihood I would end up picking one of the min-cut edges. And what this argument says is that at the beginning there are so many edges that the chances of picking a min-cut edge is relatively small, and it says basically it's 2 by n, right? But as you pick edges and then you collapse, then the number of edges becomes smaller and smaller, and so the chances, whereas the cut set, because as long as you haven't picked any of these, the number of these edges doesn't decrease, but these graphs decrease in size. So as you keep doing this, you end up in a situation where the probability that you pick one of these edges to collapse becomes high. And that's why we had to go for this second algorithm. What the second algorithm does is it basically says, okay, as long as there are a large number of edges left, I'm going to use this simple strategy. But at the point where my probability of picking one of those min-cut edges becomes slightly high, I'm going to, stop this naive process. Then I'm going to use a less naive process. What the less naive process is going to do is it's going to try 2 times. Okay, for the remaining graph, it's going to try 2 times, and in those 2 times, whatever comes up, it's going to pick up the minimum among those 2. Okay, but this is sort of a divide and conquer type, algorithm. So even though at the top level I'm doing 2 times, within each of those 2 times, I'm going to do the same strategy. So you end up going so as a result, what happens is that by the time my chance of picking one of those min-cut edges becomes really high, I have so many copies, so many places, right? So it goes from 2 to 4 to 8 to 16. So by the time I get to a point where my probability of making a wrong edge is high, I am repeating that so many times that across them I reduce the chances that I made a mistake. Okay? So, and again, by choosing the point where I make the division and the number of times I repeat, I'm able to prove that the overall complexity is actually quite good. Okay, and then once again, once you understand the intuition, the math is something that's relatively routine, and you can go back and work it out in your leisure. Okay, so the